Hello everyone, welcome to Programming Knowledge. Welcome you again all to Programming Knowledge. In today's tutorial we are going to cover about graph traversal using adjacency list. So basically in today's tutorial we are going to cover depth first search traversal recursively. So this is the one of the ways of traversing a graph. One way is depth first search and another is breadth first search. So the basic difference between the two, I have already told you that DFS uses stack and recursion, and BFS uses iteration. So this is the one of the thing, different iteration plus queue. So these are the two traversal we are going to learn. But in today's tutorial we are going to learn about depth first search. So this is depth first search we are going to do today. So let's get started with the tutorial. So this was our graph, and we have a file named dfs.py. In this we are going to cover the depth first search tutorial, and here you can see we have a graph. So basically we have seven vertices and nine edges. So seven vertices, 1 2 3 4 5 6 7, and nine edges, 1 2 3 4 5 6 7 8 and 9. So I'll quickly give an overview. A to B is connected, yes. A to C is connected, A to F is connected, then C to E is connected, C to F is connected, C to D is connected, D to E is connected, D to G, and G to F is connected. So what we are going to do first, we are going to take a graph input, and we are going to implement a depth first search traversal on this graph. So let's quickly do this. So what we can do, we can take a graph from collections. Okay, I'll move to the top. From collections, import default ticked, and before we go, I would give you a brief overview of how depth first search traversal works. Suppose we have a starting point. Let this be the starting point. A be the starting point in this graph. When we move from A to B, then we check that is the B as a node vertex, is it explorable? So yes, it is explorable, but it has a path moving back to A, but A is already visited, so we don't explore it anymore. So we have visited B. So in the same case, we move to from A, we move to C recursively, we move to C, then we move to C and check where we can go. We can go for E, then D, either F, or back to A. But since A is already visited and we can't move back to it because it is already visited, so we move to either of the nodes. And from F, I like from here we go to F. So okay, visited, mark it as visited. So from F, where we can go to G, C, A. But A is already visited, C is also already visited, we can only move back to G. Okay, so when we move to G, mark it as visited. So G is marked as visited. So from G, where we can move to D, F, but F is already visited, so we don't move. So we move to D and mark it as visited. From D, we can move either to C or E or G, but G is already visited, C is already visited, so we don't move there. We maintain an order of vertices which we have already visited, so we move to E. Since all of them are visited, so we end the recursion there. So this is how depth first search works. So that was the case. This is how depth first search works. So A would be our starting node, so this would be the starting point. Okay, so let's move with the implementation part. So simply what we are going to do, v comma e is equal to map int comma input dot split. I'll quickly take so for we have how many graph is equal to default det of list. So for I in range e u comma v is equal to map str input dot split. So I'll make a split function, then graph of u dot append v and graph of v dot append u. So this is how we have implemented our graph. So now we have our graph. Then let us make a path is equal to empty list. So this will define the path, and start is equal to a, because we are moving a as the start node. And now what we are going to do, so traversed path is equal to dfs. We'll implement the dfs function, and then I would print the traversed path. Okay, so this is the way we are going to print the traversed path. Now we are going to implement the dfs function. The first parameter is going to be the graph, the second parameter is going to be the start node, the fourth parameter would be the path, which is empty, and the third parameter is going to be visited. So I will also define a visited here. Visited is equal to default det of boolean, because we have to only maintain whether this black vertex is already visited or not. So now we are going to implement the dfs function. Okay, so here we are going to define dfs, and here I have the graph, then I have the start node, visited, and the path. So we'll complete that function. The termination condition of this dfs is if all the nodes are visited one by one. So if this is visited, 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 and visited, so the recursion would end there. So we would maintain the visited list in O of one time, because that is a dictionary. So that is a boolean value that for that vertex it is visited. And I told you that in DFS, like if the path, like if we move from A to F, so from or F we can move back from F we can move to C or G on A. We won't move back to A because it's already visited. So we move to only C or G. Okay, so let's complete this function. So now we have first path dot append start. So path dot append start, and visited, we mark this node as visited of start is equal to true. We mark this node as visited because we this is the starting node, and we append this in the path, and we mark this as visited. So this is the base case. Now we move to the recursive process. Very simple. For neighbor in graph of start, for every neighbor for that vertex, because start is the vertex. Okay, so start is the vertex for neighbor in graph of start. If if visited of neighbor is equal to false, if the neighbor is not visited, because since this is a dictionary, this would be we would check for the visited in O of one time. If visited of neighbor is equal to false, then we would recursively call the DFS graph visited path. We are maintaining the path, and here instead of start vertex we are going to put neighbor. So this is how recursion works. We define it for one base case. Okay, we define it for one base case. We start the recursion here, and now then it will do all the work recursively. Okay, then if the recursion would end, then would return the path. Okay, so let's I will copy this. Okay, so then just a second. Okay, so yeah, so I've copied the test case. Now let's have a quick overview. V comma is equal to map input of split. Then we have a graph, then u comma v, graph of u dot append v. Then we, since we define the path, start, visited, traverse path, and then let's run this file. and let's run this. Yes, now here you can see that we have got our traversal. So you can see that it has been unique, like the traverse nodes are unique. We don't have a repetition of nodes because they we have maintained a dictionary of visited. So let's analyze the time complexity of this. uh, since here you can see, since we are using a loop, so the worst case for the loop would go to v plus e edges, and this takes o of one time, big o of one time. So this would take o of v plus e. So, and this is the time complexity, so I'll write the time complexity here. Time complexity is equal to o of v plus e, and the space complexity would be o of v, because we are defined a dictionary of for every vertex, whether it is visited or not. So here you can see the time complexity would be o of v plus e, and the space complexity would be o of v, because we define a dictionary to check whether the vertex is visited or not. And but the checking is done in o of one time, because it is a simple dictionary which states true or false. Okay, so this is the output. We can quickly move to our a test case. Like if the start vertex was a, then the graph must have moved from a to b, then it has marked it as visited, then it would have said that is it explorable. No, because it is not explorable more, because we can only move back to a, and a is already visited, so we can't explore this node b any further. Then it must have moved to c, then c to e, then e to d, then D to G, and then G to F, and F, it must have gone from F, it could have gone to G, either C, either A, but all of them are marked visited, so we don't carry on the recursion more. So thank you. This was for the DFS part. So thank you guys. Thank you so much.